Section 6.5, Additional Exponential and Logarithmic Models. In this section we'll see some applications of exponential and logarithmic models. In particular, we will focus on compound interest, with periodic and continuous compounding. Talk about annuities, amortization of mortgages, and carbon-14 dating. Alright, so the first situation, periodic compound interest. The accumulated amount, A, after T years in an account with principal P invested at an annual interest rate R, expressed as a decimal value, compounded N times per year, is given by A is equal to P by 1 plus R over N to the NT. This gives us the accumulated value of a principal amount invested at a rate compounded N times per year for T years. Suppose that you want to invest $5,000 in an account. Find the accumulated amount if you invest this money at 3.5% interest compounded quarterly for 20 years. So if we are investing $5,000, then the principal, P, is 5,000. At 3.5%, R would equal 0.035. Compounded quarterly, N equals 4. Quarterly means 4 times per year. For 20 years, T would equal 20. Then the accumulated value would be 5,000 by 1 plus 0.035 over 4 to the 4 times 20. Now we don't want you to do this in your head, so let's bring up the calculator. 5,000 by 1 plus 0.035 over 4, close off the quantity and raise to the quantity 4 times 20. So $10,038.15. What if that same principal was compounded weekly for 20 years? Alright, so the principal is still 5,000. The rate is still 0.035. We weren't told anything different. But now it's compounded weekly, so now N is equal to 52, and again T is 20. So notice I just have to change that 4 to a 52. So A would equal 5,000 by 1 plus 0.035 over 52 to the 4 times 52. I'm sorry, to the 52 times 20. Alright, so now I'm going to press second enter on my calculator. That brings up that last line I typed in. I'm going to go to where I had that 4, and I'm going to insert the 52. And now I can delete the 4, and same thing in the exponent. Insert 52, and I'll delete the 4. Hitting enter. So $10,066.39. So notice that compounding 4 times per year, compounding 52 times per year, in the end it didn't make a huge difference. Right? There's only a difference of, not even $30 over 20 years. Alright, so as the number of compoundings increase, the accumulated value will increase, but depending on how many compoundings we were starting with, it might not be a huge difference in the end. How much money must you invest today if you want to see your money grow to $500,000 in 30 years at 5% annual interest compounded monthly? So here we have A, the accumulated value is $500,000. We don't know the principal. The rate is 0.05. The number of compoundings monthly, that means 12. And T is 30. So then we have 500,000 is equal to P by 1 plus 0.05 over 12 to the 12 times 30. All right, so we have 500,000 equals P times some number. So we just need to divide by that number to solve for P. All right, so let me bring up the calculator and move over a little bit so we can see. All right, so what do we have here? So I have 1 plus 0.05 over 12 and raise that to the 12 times 30. All right, so that's that number. So what this is saying is 4.4677. So 500,000 is equal to P times 4. Was it 4677? I think. All right, so now to solve for P, I just need to take the $500,000 and divide by that. So 500,000, divide that by the answer. Hit second and the negative key to bring up your last answer. Hit enter. So what's that? $111,913. So P is $111,913 and some odd cents, 30 cents. So if you just happen to have $111,000 hanging around and you can get 5% annual interest, you can have $500,000 in 30 years. If you take the periodic compound interest formula and let the number of compoundings per year approach infinity, so what we call continuous compounding, the accumulated value approaches the following. The accumulated value A after T years in an account with principal P invested at an annual interest rate R compounded continuously is given by A equals P times E to the RT, where again that E is approximately 2.718, right, the Euler number. Suppose that $5,000 is invested in an account paying 3.75% interest compounded continuously. What will be the accumulated amount after 20 years? So once we see the continuously, I know that I'm using A equals P e to the RT. All right, we aren't told the number of compoundings per year, we're told it's continuous. Alright, so our principal is $5,000, our rate is 0.0375, and time is 20. So then the accumulated value would be 5,000 by E to the 0.0375 times 20. Again, we'll use our calculator at this point. 5,000. Bring up our exponential. 0.0375 times 20. Close off the exponential, hit enter. $10,585. How long will it take a $10,000 investment to double in value if it earns 4.25% interest compounded continuously? All right, compounded continuously, so A equals P e to the RT. Now what do we know? We have the principal of $10,000. We want that to double, so the accumulated value would then be $20,000. We have the rate as 0.0425, and the time is unknown, so we need to solve for t. 20,000 equals 10,000 e to the 0.0425 t. Dividing through by the 10,000, we have 2 equals e to the 0.0425 t. Now notice that no matter what we started with, if we double it, we would have twice as much on the left-hand side. And then in solving for t, the first thing we would do is divide by our principal. And so it actually doesn't matter how much you start with to figure out the doubling time in these types of applications. Alright, so now we have 2 is equal to e to the 0.0425t. Let's use the natural log. So then the natural log of 2 is equal to the natural log of e to the 0.0425t. So then the natural log of 2, remembering our rules for inverses with logs and exponentials, that would give us 0.0425t. Dividing through it by 0.0425, t equals the natural log of 2 over 0.0425. All right, going to our calculator. Natural log of 2 divided by 0.0425, 16.3. All right, so conclusion, it would take about 16.3 years for the investment to double in value. An annuity is an investment where an individual makes regular payments into an account which accumulate interest. The goal is to have some set amount accumulated at the end of the investment. All right, so whereas before we were, plunking down some amount in the beginning and then not touching it again, now we're regularly putting in an amount of money. All right, so if P is the deposit in dollars made at the end of each compounding period for an ordinary annuity offering an annual interest rate R, compounded n times per year, the accumulated value A after t years is given by A equals P by 1 plus I to the nt minus 1 all over I, where I equals R over n is the rate per compounded period, not rate per year. Okay, so we're given the rate per year, but then in this formula we have to figure out the rate per compounding period. All right, so P, that's how much we're putting in, say, each month usually, right? Most annuities you put in an amount each month as you're saving up. As part of her retirement plan, Joanne deposits $500 per month into an annuity that will pay 5.6% annually, compounded monthly. If she pays into the annuity for 25 years, what will be the accumulated value? All right, so how much are we putting in per month? $500. Now our rate is 0.056 and our n is 12, so I is 0.056 over 12. T, the number of years, is 25. So we would have that the accumulated value is 500 by the quantity 1 plus 0.056 over 12 to the nt, to the 12 times 25, and from that we subtract 1, and then we divide that whole thing by I, 0.056 over 12. Now, on our calculators, although you don't have to do this, it might be helpful to store that 0.056 over 12 as a number. So here's one way to do that. If I type 0.056 over 12 and I press store, S-T-O, I'm going to store it under the alpha I. And it gives me that number, 0.046, etc. So now what I'm going to do to calculate this, A is equal to 500. I don't have brackets, so I'll use parentheses. I have to use another parentheses for the quantity. 1 plus, now I hit alpha I, and I need to raise that to the 12 times 25. I need to subtract 1, close off the numerator, and then I'm going to divide that by, again, alpha I. enter. $325,930. So let's just approximate to the nearest thousand. So approximately $325,930. Now, what if instead we want a specific accumulated value? All right, so now she wants the accumulated value of the annuity to be $900,000. For how many years will she have to pay into the annuity? All right, well, we have the accumulated value, 900,000. We have the value of P, which is still 500. Our I is the same. Our N is unknown. Or not N, sorry, our T is unknown. All right, so the I again is 0.056 over 12. All right, so using the same formula, we have now 900,000 is equal to P. Well, the P is 500 by, let's see, we'd have 1 plus I to the NT. And what was N? N is 12. To the 12T minus 1 over I. Alright, so let's see, to solve for this, first thing I'm going to do is take that $900,000. I'm going to multiply by I, both sides. Alright, so let's do that. 900,000 times I. That gives me 4,200. So 4,200 is equal to 500 by 1 plus I to the 12t minus 1. I'll divide through by the 500. Let's see, 4,200 divided by 500, that's 42 over 5, is 8.4. I guess I don't really need the brackets anymore. Add 1 to both sides. 9.4 is equal to 1 plus I to the 12t. Alright, now since I see the variable is in the exponent, I'll apply the common logarithm to both sides. Alright, so log of 9.4 is equal to log of 1 plus I to the 12t. Log 9.4 is equal to 12t log 1 plus I. And now to solve for t, I'm going to divide both sides by 12 times log 1 plus I. Alright, so now on the calculator, see log 9.4, close that off, divide by quantity, 12 times log of 1 plus alpha I. Close off the log, close off the denominator, hit enter, 40.1. So t is approximately 40.1. So she would have to pay into the annuity for 40 years. Alright, suppose instead that we invest a lump sum that pays out a specified amount per period while still accumulating interest on the remaining value. That lump sum is called the present value of the annuity. So if P is the payment in dollars made at the end of each period from an ordinary annuity earning an annual interest rate R compounded n times per year, then the present value for T years is given by this formula. P sub V is equal to P by 1 minus the quantity 1 plus I to the negative NT all over I, where again I is the rate per compounding period. Noah would like to retire and receive $4,500 at the end of each month for 25 years. How much would need to be invested in an account earning 4.25% to reach the goal? So how much would need to be invested? What's the present value, right? We don't know the present value. We know that the monthly payment would be $4,500. Monthly, so the number of compoundings is 12 per year, and so then I would equal 0.0425 over 12. And we know that T is 25 years. So then the present value would be P, which is $4,500, by 1 minus 1 plus I to the negative N is 12, T is 25, all over I. All right, now on the calculator, I have to set in my new I value. So that's 0.0425, divide that by 12, and I'll store that as alpha I. Alright, so there's my new alpha I. Alright, now let's calculate this. I have 4,500, I want 4,500 per month, open quantity, 1 minus open quantity, 1 plus alpha I, close the quantity, raise to the open quantity, negative 12 times 25, close the exponent, close the numerator, and divide by alpha I. So to get that, I'd have to invest right now, Noah would have to invest $830,660, 830,660. Alright, so to get $4,500 a month for 25 years, you'd have to invest, a significant amount of money, $830,000. The process of paying off a loan in regular installments over a period of time is called amortization. If P represents the principal, the loan amount, with I periodic interest rate, and N is the equal periodic payments attached to the loan, then the amount A per payment made at the end of each period is given by A equals P I over 1 minus 1 plus I to the negative N. So this is a formula that's used, if you ever go and buy a house, you probably are going to have to take out a loan on some amount of money. This amortization formula tells you how much you would have to pay each month to repay the loan over however many years. Natasha and Ed have been married for 5 years and want to buy their first home. They decide to put a 20% down payment for a $225,000 house and get a 20-year mortgage for the remaining balance. Determine the monthly payment of their home loan at 5% annual interest, excluding escrow for taxes and insurance. So just worrying about the loan. Alright, so if they're going to put 20% down on the house, that means they're going to pay that much up front. So they're only taking a loan on the remaining amount. So we need to figure out what's 80% of $225,000. Alright, so we'll use the calculator here. 80% of 225,000 is 180,000. So that's the loan amount. right? They're borrowing $180,000. All right, so that's the principal. P is $180,000. All right, now their interest rate is 5%, but we again want the periodic interest rate I. So I would be 0.05 over 12. N is the number of equal periodic payments. So we're making 12 payments per year times 20 years. That's 240 payments. So then the monthly payment A is equal to 180,000 times I over 1 minus 1 plus I to the negative 240. All right, so let's go to the calculator. Let's store our new I, 0.05 over 12. I'll store that as alpha I. All right, now let's calculate this. I'd have 180. Now let's put parentheses around the numerator. 180,000 times alpha I. You need to make sure and put that multiplication in when we're doing this. And I'm going to divide that by the quantity. 1 minus another quantity, 1 plus alpha I, close quantity, exponent negative 240. Close the denominator, enter $1,187.92. Now we could lower the payment by having the number of years go longer. So if we changed it into a 30-year mortgage, you would get a lower payment, but you're over more years. How much interest will this loan cost them? So if we think, okay, they're paying $1,187.92 for 240 payments. So 1,187.92 times 240 payments that's what, $285,100.80. Let's just round that to 285,100. So that's the total amount they're paying on a loan of $180,000. So they're paying $105,000. This loan is costing them $105,000 over 20 years. So when you borrow money, all right, eventually you pay back more than what you borrowed. And so this is something that's very important to understand when you go to buy a home. You have to think about how much, is it worth that $105,000 over 20 years? What are ways to decrease that amount? If you pay it off quicker, right? If you can pay it off over 10 years, that would raise the monthly payment, but since you're not borrowing for so long, there's less time for interest to accumulate, and so then you would pay less interest in the long term. Logistic functions can be used to model growth that is constrained by certain factors. The growth appears exponential at first and then levels off to what is called the carrying capacity of the function. So a function that describes this logistic growth of a population p at time t is given usually as p of t is equal to c over 1 plus a times e to the negative bt, where again e is that Euler number. A, B, and C are real numbers, C is positive. If b is 0, the function describes a growth model. If b is negative, it describes a decay model. And so what we see here, here's a graph of an example logistic function. It starts off, and up to here it looks exponential. But then you reach this turning point, and where it's the population or whatever value is still increasing, but the rate of change has decreased, and it starts to flatten out into what is called the carrying capacity. Right. And so the carrying capacity is some value that happens as t becomes very large. Suppose that the population of a certain species of bird is limited by the type of habitat required for nesting. The population behaves according to the logistic growth model. N of t is equal to 6,500 over 0.7 plus 32.5 e to the negative 0.064 t. Find the initial population. Alright, so the initial population, that's usually when t is equal to 0. So let's evaluate n of 0. N of 0 would be 6,500 over 0.7 plus 32.5 e to the negative 0.064 times 0. So notice that our exponent is 0 and e to the 0 is 1. So that gives us 6,500 over 0.7 plus 32.5. So that's 6,500 over, was that 33.2. I'll use the calculator here. 6,500 divided by 33.2 is about, oh, and I forgot a 0. I missed a 0 there, so let me insert the 0. So let's say about 196. What size does the population approach as time goes on? Alright, so as time becomes a large number, what happens here? If t becomes a large number, then we have e to a negative large number. So what's e to a negative large number? Well, if you think of our exponential function, e to the x did this. So as we have negative large numbers, e to a negative large number is over here. E to a negative large number approaches 0. E to a negative large number approaches 0. So then what would happen is this approaches 0, and I have 32.5 times 0, then n of t would approach 6,500 over 0.7. Now using the calculator, 6,500 divided by 0.7 is 9,285.7, so about 9,300. So let's say 9,286. Let's be more careful. Let's look at a graph of this function over time. 6,500, divide that by 0.7 plus 32.5 e to the negative 0.064 x. Nope, wrong side. And close off the denominator. Alright, so we know that, let's check our window. X, let's go from 0 to 100. I don't know for sure what's a reasonable value there, but I know for my y values, our zero population was in the hundreds, right? It was 196. So let's go from 0 to, and our carrying capacity is supposed to be 9286, so let's go to 10,000. And let's use a scale of thousands on the y-axis. And let's see our graph. Alright, and we do see that logistic graph. So notice how it's growing. It appears to be exponential, and then we hit this turning point in a sense where things change, and then it's constrained and it will eventually reach 9286. Carbon-14 dating. Carbon-14 is a radioactive isotope that occurs naturally in carbon. When an organism dies, it will no longer absorb carbon, and the amount of carbon-14 will then decrease at a constant rate due to radioactive decay. It is known that the half-life of carbon-14 is around 5,370 years. So then the equation N equals N0 times e to the negative 0.000120942 t gives the amount of carbon-14 in a sample, or N0 represents the original amount of carbon-14 in the living tissue, and t equals the time in years. Now you might wonder where that formula comes from, and it's really not too bad to figure out. Since we know it's been figured out that the half-life of carbon-14 is 5,370 years. So that means if we start with P naught, if we start with N naught, right? We start with N sub 0 at t equals 0. Then at t equals 5,370, since this is a half-life, we would have half of the original amount. So if we assume an exponential model, and we can say, okay, well, P of t is some initial amount e to the kt. Well, then when t is 5,370, then we would have half of the initial amount equals n naught e to the k times 5,370. Dividing through by the n naught, we have 1/2 equals e to the 5,370k. I just switched the order there in the exponent. We apply the natural log. So then the natural log of 1/2 is equal to 5,370k, and divide through by the 5,370. Let's see. So the natural log of 1/2, divide that by 5,370, gives us negative 1.2907. Alright, so it's a little bit different. E to the negative fourth. So there's some rounding error there, but e to the negative fourth, this is a number in scientific notation, and so this is where it comes from. Alright, so we find that k is approximately negative 0.00012, etc. Alright, so let's apply it. Suppose that a scientist wants to determine the age of an ancient tomb. She estimates that a wooden artifact from the tomb contains 58% of the carbon-14 that was initially present. Estimate how long ago the artifact was made. Alright, so we're going to start with the known formula. N equals N0 e to the negative 0.000120942. Now we need to solve for t, how long ago the artifact was made. We want t. We don't know the initial number, but we do know that 58% of the original amount remains, right? 58% of the carbon-14 that was initially present. So we have N equaling 0.58 and 0, 58% of the initial amount. So 0.58 n sub 0 equals n sub 0 e to the exponent t. Divide through by the n sub 0. So then 0.58 equals e to the exponent t. Apply the natural log to both sides. So then the natural log of 0.58 is equal to negative 0.0001200942 t, and now all I have to do is divide through by that coefficient. Alright, so let's see, the natural log of 0.58, divide that by negative 0.0001200942. So 4,000, about 4,500 years. The artifact was made about 4,500 years ago. All right, that concludes the presentation for the section.